All right, so we're diving deep into geothermal energy this time.
Sounds hard.
Yeah,
Hmm.
literally. Uh, but more specifically, we're looking at a company called Quaise Energy.
Okay.
You've probably heard the buzz about geothermal, right? It's using the Earth's internal heat
Mm-hmm.
as an energy source.
Yeah, it's a massive energy source.
Practically unlimited, really. Like almost sci-fi when you think about it.
It is, it is. I mean, the idea of harnessing the Earth's heat to power our world.
Right. But there's a catch, of course.
Right.
Most of that heat is trapped miles underground.
Yeah, too deep for us to reach easily.
Yeah, with conventional drilling at least.
Exactly.
So how do we get to that heat?
Well, that's where Quaise Energy comes in.
They claim to have a solution, and
It is a very unique solution.
yeah, it's pretty wild stuff. They're using something called a gyrotron.
A gyrotron.
Yeah, to vaporize rock.
To vaporize rock?
Yeah, you heard that right.
I mean, how does that even work?
Well, it sounds like science fiction, but it's based on some pretty solid science. Apparently, gyrotrons are already used in fusion research. They heat plasma to incredibly high temperatures.
Yeah, millions of degrees.
Yeah, millions of degrees. But Quaise is taking this technology and pointing it, well, down.
At the Earth.
Yeah,
So instead of heating plasma, they're heating rock.
basically.
Hmm.
Imagine a superpowered microwave that can melt rock.
Wow. Okay, so no more giant drill bits.
Nope. Quaise is saying goodbye to traditional drilling. They're melting their way down to those deep, hot zones.
Interesting.
And we actually got to see this thing in action.
You did?
Yeah, at their facility in Houston.
Yeah.
They had this demonstration where they just melted rock, just like that.
That must have been something to see.
It was mind-blowing. And they had these samples of the melted rock, too. It looks like obsidian almost. Really cool.
I can imagine. But I'm guessing there are some challenges when you're talking about drilling miles into the Earth.
Oh, absolutely. Like what happens when they hit water?
Yeah, water's a big one.
Because it's everywhere underground.
Yeah. Yeah, pretty much. And water absorbs those millimeter waves that the gyrotron emits, which can mess with the whole drilling process.
Right, so it's like trying to microwave something that's soaking wet.
Sort of, yeah. But Quaise has come up with a pretty ingenious solution.
Oh, yeah? What is it?
As they drill, they create this obsidian-like casing.
Obsidian.
Yeah, like that melted rock sample you saw. The intense heat from the gyrotron melts the surrounding rock, and it solidifies into this glassy sealant.
So they're basically creating their own pipe as they go.
Yeah, exactly. It's pretty amazing. It blocks any water from seeping in.
It's like nature's plumbing system.
Yeah, I like that.
But is all of this enough to make it economically viable? You know, we're talking a totally new way of drilling at crazy depths.
Well, that's the million-dollar question. But Quaise believes they can produce electricity from these deep geothermal wells at a cost that's competitive with fossil fuels.
Really?
And maybe even cheaper in some cases.
Cheaper than fossil fuels.
Well,
That's a bold claim.
it is bold, for sure. But it all comes down to something called the levelized cost of electricity, or LCOE.
LCOE.
Yeah, it compares the lifetime costs of different energy sources.
Okay.
And because deep geothermal is always on, it's a very reliable source of energy, Quaise's projections show that it could actually beat fossil fuels on price, in some places at least.
Wow. If they can really pull this off, we're not just talking about clean energy.
Right.
We're talking about clean energy that's actually cheaper than fossil fuels.
That's the dream, isn't it?
Yeah, but right now, we're still just looking at projections. What if these costs skyrocket when they actually start drilling in the real world?
Well, that's the big question mark. Those projections are based on models and lab tests.
Right.
The real test will be those upcoming field trials.
All right, so we've got this incredible energy source way down there and a potentially revolutionary way to get to it. Now it's time to see if Quaise can pull it off.
And that's what we'll be digging into in the next part of our deep dive.
We'll explore how Quaise got started, the journey from the lab to these field trials, and what's at stake as they get ready to drill into the unknown.
It's going to be fascinating to see how this all unfolds.
Definitely. Stay tuned.
So we're back talking about Quaise Energy.
Yeah, it's pretty wild to think that they're about to actually test this technology out in the field.
It is a really big moment for them.
For them, and maybe for the whole future of geothermal energy.
Yeah, it's true.
But before we jump into those field trials, I think it's worth taking a look back and seeing where this company came from, you know, their origin story.
It's a pretty interesting one.
Yeah, how did Quaise Energy even get started? Was it a bunch of, like, friends in a garage, or was it some sort of corporate thing?
It's actually a really fascinating story.
Okay.
Quaise was founded back in 2018 by these two guys, Carlos Araque and Matt Hood.
Okay.
Araque, the CEO, he has a background in energy and infrastructure.
Mm-hmm.
And then Hood, he's the CTO, and he's a drilling tech expert.
Yeah.
But the idea that really sparked it all, it actually came from an MIT scientist named Paul Waskoff.
Oh, so it started in a lab.
Yeah.
That's cool. What was he working on?
Well, Waskoff was at MIT's Plasma Science and Fusion Center, and he'd been doing these experiments using this millimeter wave energy to drill into rock.
Wait, the same kind of energy that gyrotrons make?
Exactly.
Nice.
And Arakenhode saw the potential of this for geothermal, and so Quaise was born.
So they took this idea from a fusion research lab and applied it to, well, digging holes in the ground.
Yep, pretty much.
That's amazing.
It just goes to show you how fundamental science research can lead to these unexpected breakthroughs.
Totally. Okay, so they have this really wild idea, but how did they go from like a lab experiment to actually building a drilling system?
Well, they got some early funding from a venture capital firm called the Engine.
Okay.
They're affiliated with MIT, and they focus on these, what they call tough tech startups.
Startups that are taking on really hard problems, like this
Oh.
one?
Exactly. So that initial investment, it let Quaise build a team of engineers and scientists to really develop this technology.
So they got the brains and the money.
Yeah.
That's pretty awesome.
And they really have accomplished a lot in a short amount of time.
Yeah, that's true. But they're still a young company compared to like the big giants in the energy world, right?
Yeah, that's true.
So these upcoming field trials, that's really where the rubber meets the road, you know?
Yeah, they're really going to have to prove themselves.
What exactly are they hoping to show the world with these trials? What are like the make or break things they need to prove?
The most important thing is proving that their system actually works in the real world, not just the lab.
Right, because they've done the lab tests in controlled environments.
Exactly.
But drilling through the Earth's crust, that's a whole other challenge.
It is, and it's not like they can just dig a practice hole a few miles deep just anywhere.
What are some of the challenges they might face out there?
Well, for one thing, the rock formations are going to be much more varied and complex than they are in the lab. Different types of rock, different densities.
Yeah.
They could run into unexpected geological features.
I'm sure there are a lot of unknowns down there.
Yeah, they'll need to show that the technology can adapt to those unexpected things.
Right. I bet drilling through solid rock is no easy feat.
Oh, and remember that obsidian-like casing we were talking about?
Yeah, the melted rock sealant.
Yeah, that's really going to be put to the test.
What do you mean?
Well, if it doesn't hold up and water keeps seeping in, that could really mess things up.
Oh, yeah, that makes sense. So these field trials are kind of like a high-stakes science experiment in a way.
Yeah, they really are.
And what if things don't go according to plan? Are they prepared for setbacks? I mean, it's bound to happen, right?
Well, every new technology has its hiccups, right?
That's true.
What matters is how they learn from those setbacks.
Yeah.
The data they gather, it'll either validate their approach or reveal where they need to adjust things.
Right. It's all part of the process.
It is.
I bet the whole world will be watching to see how it goes.
I think so. The stakes are high.
If they are successful, what kind of impact could this have? I mean, this is a whole new way of accessing geothermal energy.
The implications are huge. It could open up vast new areas for geothermal development.
Wow.
Places that were off limits because they were too deep or too difficult to drill with traditional methods.
Some more clean energy potentially in places that haven't had access to it before?
Exactly.
It's amazing.
And don't forget about the possibility of retrofitting existing power plants.
Oh, right. Like taking old coal or gas-fired power plants and converting them to geothermal.
Yeah, giving them a new lease on life as clean energy producers.
That would be a major win.
It would be a huge step forward in the fight against climate change.
Absolutely. But I'm also curious about, like, the broader implications. How could this change the current energy landscape? I mean, we're so reliant on fossil fuels right now, it's hard to imagine a world without them.
It is, but if deep geothermal becomes widely available and cost competitive, it could really shake things up.
So you're saying it could even challenge solar and wind, but those are already growing so quickly. I mean, aren't they already on the rise?
They are, and they'll still play a big role, but you have to remember geothermal has one big advantage over them. It's a baseload power source.
Right. It's always on.
24/7, unlike solar and wind, which depend on, well, the weather.
It provides that steady, reliable flow of energy that our grid needs.
Exactly.
So are you saying it's like nuclear power?
Sort of, yeah. Nuclear also provides baseload power, but geothermal doesn't come with the same risks.
Like the risk of accidents or the whole problem of radioactive waste?
Yeah, exactly.
So it sounds like deep geothermal could really be that missing piece of the puzzle in this whole energy transition thing, moving towards a cleaner future.
It could be.
But even with all the potential benefits, I have to ask, What are the potential downsides? I mean, there's no such thing as a free lunch, right?
You're right, and that's something we need to explore carefully.
Okay.
Every new technology, it comes with its own set of risks and challenges.
Right.
And in the final part of our deep dive, we're going to get into the potential downsides of deep geothermal.
Okay, can't wait. So we've been talking about all the potential benefits of Quaise's approach to geothermal. But now it's time to flip the script
Okay.
and talk about the potential downsides.
Right, got to look at both sides of the coin.
Yeah. What are some of the environmental impacts we need to think about when we're talking about drilling miles down into the earth?
Well, one thing that often comes up is induced seismicity.
Induced what now?
It's a fancy way of saying earthquakes.
Earthquakes.
Yeah. But earthquakes that are triggered by human activity,
Oh, okay. So we're talking about like
Yeah.
man-made earthquakes.
basically.
So how big of a risk are we talking about here? Are we talking like those disaster movies where drilling causes these massive earthquakes?
Thankfully, it's usually not that dramatic. The earthquakes caused by geothermal operations are usually much smaller than the ones you see in movies.
Okay, phew. But any earthquake is not ideal.
Yeah.
What can they do to lower the risk?
Careful planning is key.
Okay.
They have to do these really thorough geological surveys to pick spots with low seismic activity and avoid any fault lines.
Yeah, that makes sense.
And then during the actual drilling, they monitor everything super closely for any signs of seismic activity.
So they're taking this seriously.
Yeah.
Are there any other environmental things we should be thinking about?
Well, another potential issue is the release of gases during drilling.
Gases. Like what kind of gases?
Deep underground, you can find these pockets of gases like hydrogen sulfide.
Is that the rotten egg smell?
Yeah, that's the one. It can be toxic too.
Not good.
But the good news is these gas releases can be managed. They can capture and treat the gases as they come up to minimize any environmental impact.
So they're not just letting it all escape into the atmosphere.
No, definitely not.
What about water usage? I've always heard that geothermal energy needs a lot of water.
That's a common misconception. Quaise's system is designed to be a closed loop.
Closed loop, what's that?
The water circulates within the system and gets reused. They're not drawing tons of water from the environment.
So no big water guzzling plants?
Yep. Nope.
Okay, that's good.
Water conservation is a big part of their approach.
Okay, so let's talk money. We've talked about the potential for deep geothermal to be cost competitive, but what are the economic risks?
Well, one of the big unknowns is the actual drilling cost.
Yeah, the projections look good on paper.
Right, but once they start drilling in the real world, they could run into all sorts of unexpected things that could make it more expensive.
Okay, so those field trials are going to be super important.
Absolutely. That's where they'll get a real sense of the costs.
And what happens if those trials show that it's way more expensive than they thought? What's their plan B?
It depends how much more expensive
Yeah.
we're talking. They might have to tweak the technology, make the drilling process more efficient, maybe even look for more funding.
A lot of moving parts.
Definitely.
Are there any other economic roadblocks they might hit?
Well, regulations could be a factor. Getting permits and approvals for geothermal projects can be tricky.
Right. Every country has different rules.
Exactly.
So even if the technology works, they might get stuck in bureaucracy.
That's possible.
And then there's public perception, right? People might be wary of this new technology.
That's a good point. They'll need to be really transparent and address any concerns people have to build trust.
Show that deep geothermal can be done safely.
Exactly.
So it's not just about the science, it's about the social and political stuff too.
It's the whole picture.
But if Quaise can figure all of this out, they could really change the energy game.
No doubt about it. Deep geothermal has enormous potential.
Well, we've explored the incredible potential of Quaise's approach, and we've talked about the risks and challenges too.
It's been a really interesting deep dive for sure.
Yeah, it has.
It shows us that the transition to clean energy won't be easy, but companies like Quaise are leading the way.
They're pushing the boundaries, they're taking risks, and that's what we need to see.
Absolutely.
We've talked about the science, the potential, the challenges, and now as Quaise gets ready for those field trials, the world is watching. Will their vision become reality? Only time will tell, but it's definitely a story worth following.
It is. And it makes you think, if they're successful, how will it change our world? How will it change how we get our energy, our economies, our relationship with the planet? Something to think about, isn't it?
It is. And that wraps up our deep dive into Quaise Energy and the future of geothermal. Thanks for joining us, and as always, keep those minds curious.